All right, let's jump right in. Today in our explainer, we're talking about a concept that, honestly, probably still sends a little shiver down the spine of anyone who remembers high school algebra. Yeah, I'm talking about logarithms. But don't worry, we are definitely not here to memorize boring formulas. Actually, scratch that. We're going to look at logarithms from a completely different angle. I want you to think of them not as some abstract threat from a textbook, but as a mathematical Swiss Army knife. It's this brilliant, absolutely crucial tool designed to make incredibly complex, and sometimes seemingly impossible, problems surprisingly simple.
Have you ever stopped to wonder about this? I mean, how do engineers actually manage to work with quantities that span millions of units, handling huge ranges effortlessly? Or how do programmers evaluate the complexity of algorithms when they're sorting through massive, mind-boggling arrays of data? How is it even possible to multiply monstrously large numbers using nothing but simple addition? Or if we step into the realm of higher math, how do you take the derivative of a function where both the base and the exponent are variables? It sounds like a total intellectual dead end, right? But this is exactly where our Swiss Army knife steps onto the stage.
Okay, part 1, reversing growth, the exponential U-turn.
So to really understand logarithms, we first need to understand their exact polar opposite, the exponent. Picture a real-world scenario with me. Think about a viral meme spreading on social media. Let's say the number of posts featuring this meme literally doubles every half hour. We start with 100 original posts. The big question is, how much time will pass before the number of posts hits 3,200? We know this growth is like an avalanche, right? 100, then 200, 400, 800, and so on. Mathematically, what we're doing is solving the equation 100 times 2 to the power of x equals 3,200. If we simplify that down, we get 2 to the power of x equals 32. And right there, sitting up top, that exponent is what we're looking for.
Now, in simple cases like our meme, we can probably just guess that 2 to the 5th power is 32. That means 5 half-hour intervals have passed, so 2.5 hours. Easy enough. But what if the numbers aren't so clean? Notice the visual contrast here. The exponential form pushes our unknown variable x way up high, totally out of reach for normal algebraic operations. The logarithm, however, it's an elegant inverse function. It grabs that awkward exponent and smoothly pulls it down to earth, turning it into a regular number we can actually work with. At its core, a logarithm answers just one simple question. To what power do we need to raise the base to get a specific number?
Moving right along to section 2, identities, and how we go from multiplication to addition.
Let's lay down a couple of ground rules, some absolute base truths. The logarithm of 1 to any base is always 0. Why? Because any number to the power of 0 is 1. The logarithm of the base itself is 1. But here is the most important takeaway. Logarithms and exponentials are inverse operations. Just like multiplication undoes division, they cleanly and beautifully cancel each other out. If you raise a base b to the power of the logarithm of x with that same base b, you just get x. This ability to perfectly undo one another is the absolute foundation of all logarithmic magic.
And this brilliantly illustrates their main superpower. Look at these 3 laws. The product rule takes complex multiplication and literally drops it down into simple addition. The quotient rule turns division into subtraction. And the power rule? It takes an exponent, even really nasty negative or fractional powers, and turns it into straightforward multiplication. Think about what this meant before computers existed. Engineers and astronomers literally saved years of their lives by using logarithm tables to add numbers together instead of doing massive multiplication by hand. A logarithm basically acts as a cheat code that always steps math down one level of difficulty.
And this algebraic beauty is perfectly reflected in geometry too. Check out the curve of the function y equals e to the power of x. That famous Euler's number e is the ultimate base for continuous growth. To find the exact slope of the curve 2 to the power of x, mathematicians use the natural logarithm, which is just the logarithm with base e. The curve here clearly shows how the natural logarithm of 2 seamlessly links fractional powers right back to our fundamental base of continuous growth. It is literally the perfect bridge between algebra and calculus.
All right, section 3, changing the base and why this is a huge deal in computer science.
Imagine you only speak French, and the person you're trying to talk to only speaks Japanese. You're going to need a translator, right? Well, in mathematics, the change of base formula is that universal translator. It lets you take a logarithm with any weird, awkward base b and convert it into any other base you want, usually the natural logarithm or base 10. The rule is brilliantly simple. You just divide the logarithm of the number by the logarithm of your old base. So for example, to get a computer to calculate the base 2 logarithm of 100, we just divide the natural logarithm of 100 by the natural logarithm of 2.
And what's truly fascinating about this conversion trick is that it's absolutely indispensable in computer science. In the computing world, everything's built on twos, right? Zeros and ones. So algorithms, especially when we're trying to evaluate the complexity of searching and sorting through massive data arrays, rely heavily on the binary logarithm, base 2. But here's the catch. Most standard computers and calculators are hardware programmed to only calculate natural or base 10 logarithms natively. So this change of base rule, it acts as a critical lifeline. It literally allows processors to translate binary logic into operations they can actually physically run.
Which brings us to Section 4, Logarithmic Growth, Taming Infinity.
Just take a second to appreciate the sheer, unfathomable scale of the number you are looking at. This is the 44th Mersenne prime. To put this into perspective, if you tried to print this number out on paper, you would literally need volumes of thick books. It's got over 9.8 million digits. The human brain just is not wired to directly comprehend a quantity that vast. But here is the crucial point. Logarithms tame these giants. Using that exact same logarithmic identity we talked about, the one that turns exponents into multiplication, we can take that massive exponent of 32 million, multiply it by the base 10 logarithm of 2, and boom, we get a highly readable power of 10. In just a couple of quick steps, we've wrestled a 9.8 million digit behemoth down to earth by translating it into scientific notation. This is exactly why engineers and data scientists love logarithmic scales. It's what allows us to plot the tiny size of a microbe and the massive distance to a faraway galaxy on the exact same graph.
And here is another fundamental truth you should take away from this. In calculus, when we study limits and look at what happens as numbers approach infinity, the logarithm always loses the race. If you compare logarithmic growth to any power or root function, log growth is fundamentally slower. This is the exact reason programmers throw a party when the complexity of their big data sorting algorithm is evaluated as O of log n. It means that even if their dataset explodes and increases millions of times over, the program's running time is only going to increase by a tiny, manageable fraction.
And finally, Section 5, Logarithmic Differentiation, or how we solve the impossible. Okay, we've reached the final boss of today's explainer. Take a look at this function. Y equals x raised to the power of x. Try taking the derivative of that. The standard power rule? Nope, doesn't work. The exponent isn't a constant. How about the exponential function rule? Also completely useless because the base isn't a constant either. Both the base and the exponent are variables. For anyone using classic calculus rules, this is a literal dead end.
But let's move forward and see how this builds, because we have a 4-step superpower. Step 1, we just take the natural logarithm of both the left and right sides. Step 2, and this is where the magic happens, we use the properties of logarithms to drop that awkward exponent x straight down. Now our equation is the natural log of y equals x multiplied by the natural log of x. Multiplication. We just turned an unsolvable exponent problem into a simple product. Step 3, we use implicit differentiation and the standard product rule. And step 4, we just solve the resulting equation for our derivative, dy over dx. The result is stunningly compact. What started out as an impossible calculus nightmare was, thanks to logarithmic differentiation, totally reduced to a few lines of basic algebra. The logarithm literally untangled a knot of variables for us, allowing us to see right inside the rate of change of a highly complex function.
So look at what we've covered today. We've seen how logarithms reverse exponential growth, how they step complicated multiplication down into simple addition, how they translate computer algorithms so processors can actually use them, and how they solve problems that totally break the standard rules of calculus. Logarithms aren't just some abstract textbook torture. They're a completely direct, practical way to make the complexity of the world manageable. And it really makes you wonder, doesn't it? Where else in the vast complexities of our universe, whether it's in physics, economics, or biology, are similar, elegant mathematical mirrors waiting patiently for their moment to turn the unsolvable into the strikingly simple? I'm going to leave you with that thought. Thanks for joining me on this explainer, and we'll see you next time.